Singularity. Great. Here we go. Yeah. And so I've been with the Singularity slash Apptainer container community really since the beginning. I worked as the release manager for Apptainer for a while, and now, as Justin said, I'm a solutions architect at CIQ. Today, I'm going to be talking about kind of some of the things that have changed and have evolved and become different in Apptainer over the past few years. So this won't be really an introductory discussion. I'm going to assume that you've got some knowledge already about containers within HPC. But if you want more information about containers generally, or you want support or anything like that, or more questions about some of the things I talk about today. So CIQ, the company that I'm working for, is the company which is supporting the Apptainer project. We also support some other pretty high profile projects like Rocky Linux, for instance. We support Werewolf, which is an HPC provisioning system. Mountain, which is a distribution and automation system, and then Fuzzball, which is a container orchestration system, which I'll be talking a little bit about today. Okay, so today I'm just going to be providing some updates on some of the things that have changed in Apptainer over the last several years. Okay, so the things I'd like to cover today, kind of the high points as I see it over the last several years, are number one, Apptainer is now able to leverage the user namespace within Linux to do several things. One of those is to allow users to safely pretend that they have privilege within the container, even if they don't have privileges within the host system. And another thing that this allows us to do is run Apptainer completely unprivileged. I'm going to talk about MPI a little bit, and I'm going to talk about some new recommendations that we have at CIQ and some things that we're experimenting with a little bit, and then talk about how that relates to running MPI within containers. I'm going to talk about something called ORAs, which is the OCI Registry as Storage protocol, and how its increased adoption within the container landscape allows you to work now with native CIF files instead of having a hybrid approach and working partially with OCI containers and partially with Apptainer containers. And I'm going to give you an example of how this can help you secure your software supply chain. And then finally, I'm going to talk a little bit about container orchestration. And instead of container orchestration for services, which is what we normally think of with container orchestration, I'm going to talk about container orchestration specifically for jobs and from an HPC perspective. And I'm going to show you a new project that we're working on at CIQ called Fuzzball, which is specifically for this type of orchestration. Before I jump into any of that, though, what I'd like to do is just kind of recap very, very quickly some of the history of Singularity slash Apptainer. So around 2015, and many of you will already know this, many system administrators and staff scientists, myself included, began to get questions from our users about, can we install Docker on the HPC environments that we help to administer? And it was from those requests that Greg Kurtzer at Lawrence Berkeley National Labs and a group of other people as well got together and began to say, well, we can't install Docker in these multi-tenant high-performance computing environments because it's not really an appropriate tool. But if we were to provide containers for the HPC community, what would that look like? And that's really where Singularity began, is an effort by HPC people for HPC people to provide containers within an HPC environment. So that was kind of like the beginning of Singularity. Now, I've been talking about Apptainer, so you may be wondering, what's the relationship between Apptainer and Singularity? Well, a few years ago, several community members got together and went to the Linux Foundation and said, would it be possible, Singularity's become a pretty stable and mature project at this point in time. Would it be possible for you to take Singularity and sponsor it as a project? And the representatives of the Linux Foundation said, yeah, that would be fine. We would like to do that. However, really the name Singularity is kind of ambiguous, and it's got a little bit, it's linked to some corporations and things right now. And at the Linux Foundation, it's their stance not to sort of advance any one company over another. So they asked us to change the name. And so we, a few different names were advanced, we voted, we decided on Apptainer. And so really, Apptainer is the Linux Foundation supported project of Singularity. So Apptainer is Singularity, just now under the Linux Foundation. So that's where that name change came from. Okay, so the first thing I'd like to talk about as far as changes to Apptainer over the last couple of years is the way in which we're leveraging the user namespace. So if you look at the man page for namespaces, you'll see something like this. Namespaces, I'm going to zoom in on this portion here. Namespaces are a really important concept within containers. So namespaces are the way in which containers cordon off resources into one little namespace versus another. And by taking namespaces and kind of lumping them together, this is kind of how containers work. Well, there's kind of a special namespace called the user namespace. And it's special for a few reasons. One of those is that the resource, which is virtualized inside of a new namespace, in this case is actually UIDs and GIDs. So what this allows you to do is map a UID on the host system to a different UID within the namespace. And in practice, what that's typically used for is to map a UID like 1001 or whatever to 0 within a new namespace and pretend to be root. That's a pretty common use case for this. Another special thing about the user namespace is that you don't require privilege to set one of these namespaces up. Any user can do this. So Apptainer is leveraging the user namespace in a couple of ways now. One of those ways is at runtime to allow a user to become root or fake root inside of a container, even if they don't have any privilege on the host system. So I'm not going to actually show you live demos today. I'm going to show you some screenshots, but I'm going to kind of demonstrate with screenshots what this looks like. So let's say I'm here on a host system and I run ID, and you can see that my UID is 1001. My name is demo user. If I do a print working directory, you can see that I'm in my home directory. If I create a file and then I list the file, you can see that I created the file and it's owned by me. So that's nothing surprising there. Now I'm going to go ahead and enter a container. I'm going to use the shell command to enter an Alpine container with the fake root option. When I do that, my prompt changes to indicate that I'm inside the container. And if I run ID again, you can see now that my ID, my UID is 0. So I've become root inside the container. Now, if I print my working directory, it says that I'm in my home directory, which is root because I'm the root user. However, if I do an ls-l, you can see that file that I just created. Now, remember, if you've used Apptainer, that by default, when you enter a container with Apptainer, it bind mounts your home directory into the container by default as a convenience for you. So this is why I'm still able to see this file, even after I've entered the container. But notice that now it says it's owned by root. So this is a little fiction which is going on. So number one, I can still see this file, meaning that this root home directory, that's not really /root. Really what's happened is that Apptainer has bind mounted my user's home directory into the container and changed its name to root. And now it's telling me that files that I previously owned are now owned by root and that my UID is 0. I can create a new file, so I can touch another file here. And if I list those files, I can see that both files are there. They both look like they're owned by root. And now if I exit the container and I list those files, note that both of the files are still there and both of them are actually owned by me. So this is all handled by the kernel, and this is all handled by the user namespace. And importantly, if you're an administrator, the kernel is able to keep the mapping between UID 1001 and UID 0 inside the namespace straight in such a way that even though this user now has privilege inside the namespace, if they were to try to interact with any files on the host in ways in which they don't have privilege to do, the kernel will still prevent that from happening. They'll still prevent them from doing that. So this is kind of a cool new feature that Apptainer has, just leveraging user namespaces. This can also be used for the build process. And in fact, it's used by default. So you don't have to pass any fake root option anymore. It's implicitly used now. If you try to build a container without privilege on a system where the user namespace is enabled, it will default to giving you fake root access within the container when you build it. So I'll show you how this works here. So if we cat out an example definition file that I have, in this definition file, I'm starting from Rocky Linux 8 from Docker Hub. And then in the post section, I'm going to run who am I? And then I'm going to run some DNF commands that would normally require privilege to run. Okay, so now you can see that I'm running Apptainer build. I'm not doing this with elevated privileges, so no sudo. I'm not passing the fake root option. And I'm building this example CIF file from this example definition file. I've done this, I should have showed you, but I used an environment variable to silence the normal informational messages that you would get from Apptainer during the build. So we're just seeing, just the actual build process happen here. But the first thing that runs is who am I? It says I'm root, even though I had no privilege on the system when I ran this command. And now we're doing DNF update. You can see that this is working appropriately. The build will finish, and it'll tell me what it installed, and now I'll have a container built. So this is actually really, really great for users, because now this means that they can build their containers directly on the same high performance computing systems where they're ultimately going to run these containers. And so they no longer have to spin up a virtual machine or go to some other environment and build their container with privilege. Building your container with privilege is kind of an inherently risky operation. So we've been suggesting for some time that if you did that, you were supposed to do that within a disposable VM. Now this makes it a lot safer to build your containers, because you're not doing so with any actual privilege on the system. You're just building your containers with sort of a faked privilege within the container itself. So it's a lot safer. And then finally, the final way in which the user namespace is being leveraged. So I've just showed you ways in which the user, the ultimate Apptainer user, can leverage the user namespace. Actually, Apptainer itself, in its own runtime, is also leveraging the user namespace. And so now, because of that, the default Apptainer installation is now unprivileged. So it used to be that when you installed Apptainer, it came with a setuid binary, which allowed it to elevate privileges in order to carry out specific operations. Now, and you can still install it that way if you want to, but now by default, Apptainer is going to install without that SUID binary. It's going to use squash fuse to mount the squash fs file system, which has your container root file system in it within the CIF file. And it's going to use the user namespace. It's going to enter that user namespace to gain the privileges that it needs to create a new mount namespace and to do all the mounting operations and everything to present the processes inside the container with that new root file system. So it will leverage the user namespace and other tools that exist on the system, rather than trying to leverage a set UID bit workflow and escalate privileges in that way. Okay, now because you can now install unprivileged versions of Apptainer, it's now no longer necessary for you to be a privileged user to install Apptainer itself. So now unprivileged users can install Apptainer all by themselves without needing to have privilege to do so. And in fact, our release manager, Dave Dykstra, working at Fermilab, has created a helper script which is here at the GitHub repo. If you go into tools, you can find this install unprivileged.sh, and it will allow users, if they download this and run this, to install Apptainer with its dependencies in whatever directory they want to do so, a completely self-contained and relocatable installation. So it's important as a it's important as an administrator to realize that your users now, if you have the user namespace enabled on your system, that your users now have the ability to install their own versions of Apptainer. This is because if you are using things like an execution control list on your system to control which containers can be run and which can't, or if you are, disabling maybe like the PID namespace, for instance, within your configuration files, or if you have some other configuration, it's now possible for your users to install their own versions of Apptainer with their own configuration files and to render this configuration invalid. So if you have specific configuration needs and you require that your users must use a central installation of Apptainer, you're going to have to put some procedure in place to make sure that users have to use that version of Apptainer. You might have to disable the user namespace in your system to enforce that. Okay, now I'd like to switch gears a little bit and start talking about containerized MPI jobs. So in this section, I'm going to, kind of recap some of the difficulties that containerized MPI jobs can present to users and to administrators. One of those is the wire up problem, which I'll, revisit and kind of recap. And the other one is problems having to do with high-speed interconnects or fabric adapters. I'll talk kind of briefly about historical approaches to solving these problems and why they're difficult and why they ultimately lack portability and kind of defeat some of the reasons that containers exist. And then I'm going to talk about PMI and libfabric and how we're now recommending that users use these technologies to try to make it easier for them to create their containers and increase their container portability. And I'm also, going to briefly mention, I'm not really going to talk about it, but I'd like to mention that there are container-friendly package managers like SPAC, like EasyBuild, like GUIX. You can use these package managers to install applications directly on your host system, but you can also create containers out of these. And these can greatly reduce the difficulty associated with creating a definition file for an MPI-enabled workflow. So you should really think about these and look at these if you're using MPI in your system. Okay, so let me just review the actual problem and the difficulty that arises first with wire up of a containerized MPI job. So let's just think about MPI for a second. So the way that MPI works is that, you're on a node where you're going to submit your job from, and then you've got some compute nodes that your jobs are going to run. So in order to submit your job, you'll use like an MPI exec command or something similar to that. Maybe some options and arguments, and then you'll specify a process that you want to run with the MPI exec command. When that happens, MPI is going to reach out via SSH or RSH to all these compute nodes, and then it's going to go ahead and start that process on all the compute nodes. They're going to be assigned rank, and they're going to be given the information they need to start message passing and communicating with one another via the same MPI implementation. So we have MPI running here at the submission stage, and then we have MPI running here to enable the interprocess communication or the message passing. So this can be referred to as wire up. The stage of the MPI can be referred to as wire up. So let's see what happens when you try to do that from within a container. The problem is if you try to do MPI exec and then the name of some process, MPI exec will reach out of your container and SSH to all these different compute nodes. But importantly, it SSHs outside of the container. So now you've kind of escaped the container when you do this. And so now it can't find the process that it's supposed to start because that process exists inside the container that it doesn't have any access to. So historically, the way in which we have suggested that you should, fix this problem is by having MPI inside your container and also having a matching version of MPI outside your container on the host system. And these two MPIs are supposed to work in concert with one another. You can either install MPI inside your container or you can bind mount it in at runtime. What this looks like is that then on the submission node outside of a container, you run MPI exec, and instead of just running the name of a process, you run now an Apptainer command with some options and arguments, and you point it to a specific container and then specify that you want a process to run inside the container. So this happens outside of a container. MPI then goes to all the nodes, and it starts, because you've given it this Apptainer command, it starts containers with the processes running inside. And by virtue of the fact that MPI exists within these containers, they're able to finish the wire up process and begin communication with one another. Now, in order for this to work properly, I mean, this looks like a great solution in theory, but in order for this to work properly, this MPI, which is handling the message passing between the processes on the compute nodes, has to match exactly the MPI which is running on the host. And that's a problem because the user then who builds this container has to know the type of MPI which is running on the host, the exact version, and also they have to have some details about the compilation arguments which were used to create this MPI in order for them to be able to create a compatible MPI inside the container. And so that's difficult. And then even after that process has been carried out, it creates a container which is now not portable. So the problem is now if this MPI changes on the host, or if the user decides that they want to take their container to another cluster and run it there, it's not going to work anymore. It's going to break. So we are now suggesting, and we are experimenting and benchmarking with a solution that uses PMI. So PMI, process management interface, I believe, is a standard that lays out how this wire up process should occur. And so because of that, because there's a standard that exists, you can have a tool like Slurm, for instance, on your cluster that has PMI support. And so now your workload manager can actually understand how to kick off the wire up process itself. And so what this looks like is now, instead of doing an MPI exec command, I can just call srun with Slurm, for instance, and I can specify that the MPI that I want to use is PMI2 in this case, and then I give it that Apptainer command. Now in this case, srun is causing this SSH to occur, and it's firing up this containerized process. And now, as long as the MPI which is inside my container has been compiled with support for PMI2, then I'm able now to establish communication between all these processes. So now you don't even have to have MPI installed on the host system at all, as long as you have a tool which has been compiled with PMI support on the system, and as long as your MPI implementation has been compiled with that same PMI support, in the container. Okay, so my colleague Jonathan Anderson is the person who has really been responsible for looking at this at CIQ, and he's currently, as far as I know, performing a bunch of tests and benchmarks and trying to figure out under what situations this procedure works and under what situations it'll negatively impact performance. And so we're still fairly new in looking at this and trying to suggest this, but I think that we're probably going to end up updating the Apptainer documentation to reflect this new suggestion or this new recommendation for how we should run MPI jobs. And this is not the first time that I've talked about this. So we recently published a blog post. These links are going to be available in the slides that I circulate later. So we recently published a blog post that's got a lot of details about this method and how to implement it. Jonathan actually spoke at the most recent HPC AI Advisory Council meeting at Stanford on this. And then we did a webinar at CIQ where Jonathan and I discussed this approach a few weeks ago. So these links, once again, will be available to you after the presentation in the slides that I distribute. Okay, the second major hurdle to overcome with containerized MPI jobs has to do with the fabric adapter. So let's say we're on a compute node and we've got, InfiniBand or an OmniPath card in the compute node. And this is, the actual hardware. So in order to run that hardware, we have a kernel, and the kernel has modules which are compiled in order to interface with that hardware. Now, remember, when you run a container, one of the basic technologies behind Linux containers is that they share the kernel with the host system. So if you share the kernel with the host system, you also share, of course, the kernel modules, which are loaded into the kernel when you're running. And so this is one of the base technologies which allows containers to run so quickly and with such little overhead, is that they don't need a separate kernel. They share the kernel with the host. Now, of course, there are user space libraries which interact with the module. They're driver libraries that interact with the kernel module, and those are going to be in your container. And then on top of that, we have an MPI implementation, and on top of that, we have an MPI-enabled application. Now, the problem with fabric adapters when it comes to containerized MPI is that, of course, the MPI-enabled application is tightly coupled to the MPI implementation because it's compiled against it. And here's where the issue arises. In some cases, the MPI implementation itself might be tightly coupled to the user space driver libraries because it's compiled and linked against them. And of course, the driver libraries are tightly coupled to the module, the underlying module, because they have to be. So you can end up with a situation in which your MPI-enabled application is tightly coupled all the way down to the kernel, which is running outside of your container. And so now your container is tightly coupled to a specific kernel or a specific module, rather, that may be loaded into the kernel. So this makes your container not portable, and it makes your container brittle. If this module is updated, your container will no longer work. So we have been experimenting with and suggesting that instead people more widely adopt libfabric when they are using containerized MPI. So now your MPI implementation is now compiled against libfabric, but libfabric provides an abstraction layer so that it doesn't matter quite so much, what version of the module is installed or even what kind of underlying fabric adapter you have. Libfabric is able to translate, the commands into the proper into whatever is proper for the underlying kernel module. So once again, this is something that we're experimenting with and benchmarking currently at CIQ. So far, our early experiments have shown that this, at least in our hands, this isn't really producing too much of a detriment as far as job performance. So we think that this is going to be a good route moving forward, and ultimately we'll probably update the Apptainer documentation to reflect this. Okay, I'd like to shift gears again now and start talking about ORAs and how that, yeah.
Yeah, Dave, this is Justin. I just wanted to point out that there are a few questions that are stacking up in there that might pertain to what you were just Paula has a question about the versions of Apptainer. Are there restrictions on which versions would be needed for certain functionality that people need to keep an eye on?
Oh, okay. Yeah. Thank you for alerting me to that. I haven't really been seeing the chat. Okay. So let's see. Paula, so is this available? I'm sorry. So I've covered a lot of ground at this point.
Yes, sorry, because now it's out of context. For my question was related to when you're doing the fake root and having the like ls, and you would see the root as user and owner and group.
Yeah, thank you. Okay, thank you. So that was introduced. I actually can't remember when that was introduced. That was introduced some time ago. So it was probably Apptainer version 1.1 point something, and we are now at 1.2. So it's been maybe a year and a half, 2 years ago that was introduced. I think what's actually new is that the user namespace, the underlying technology which enables this, is becoming more and more prevalent. So in Enterprise Linux 7, it was present, but it was disabled by default. In Enterprise Linux 8, it's now present, but I don't know if it's present in its most complete and full featured form, but it's being adopted, more and more.
Great.
All right, thank you.
The unprivileged install looks like it only works on certain distributions. What about Ubuntu Debian? Yeah, so I don't know if that actual installation script provides any support for anything which is outside of Enterprise Linux. I kind of doubt it because it's RPM based. So Dave Dykstra, in addition to being our release manager, also handles RPM packaging and EPEL. And so because he has that expertise, that's how he was able to write that script. However, I think that if you were on Ubuntu or Debian and you wanted to do an unprivileged installation, I think you could accomplish that simply by building from source. And when you did the configuration, you would just point it to a directory where you've got write access as an unprivileged user.
Great. And Dave, just to remind you, we need to wrap up by 2 o'clock, and it'd be good if we had a moment for some more questions too.
Sure.
But it looks like Martin is just pointing out that it was Apptainer 1.1.0 for the user namespace.
Thank you, Martin.
Yep. Go ahead. Thanks.
So the third one, I actually might have gotten it wrong. There's a third. So SPAC, easy build, and question mark. I think I said GUIX, but I think that might be incorrect. There is a third. And I'll have to look back again and figure out what the name of it is. There's a third HPC kind of centric package manager, which I was recently introduced to. And I was kind of interested in what that was, but I can't remember the name off the top of my head. Let's see, it was an Apptainer 1.1.0, and the user namespaces were set as default. Yeah, thanks. And then Charlie Cloud. I don't know if that's a question. So there is another container platform which I won't actually be covering today because I don't have much experience with it, called Charlie Cloud. There was around the time that Singularity was first being developed, there were a few different projects. There was Singularity, Charlie Cloud, and Shifter, which were all sort of geared toward HPC. The one that I've got the most experience with, obviously, and I've had the most interaction with is Apptainer, so that's the one that I'll be covering today. It's my understanding Charlie Cloud is a little bit it has the opposite philosophy from Apptainer. Apptainer is supposed to be very, very full featured and kind of do everything for you that you need to do, which has pros and cons. And I think Charlie Cloud is supposed to be a little bit more lighter weight and a little bit more do-it-yourself, which also has pros and cons. Okay, so I'd like to shift gears now and start talking about ORAs and software supply chain and kind of introduce some ideas to you about this. So ORAS stands for the OCI Registry as Storage, and this is a protocol which allows you to push basically arbitrary data to an OCI registry like Docker Hub. this has also, it's been around for a while, but it is increasing in its adoption. So Docker Hub, just within the last year or so, started to allow people to push CIF files, native CIF files created by Apptainer up to Docker Hub. The great thing about this is that, there's some advanced features that you can use with the Singularity image format or CIF files that include things like signing and verifying your containers and using encryption. And now you can do that, and you can still use an OCI registry. So you can take advantage of the advanced features of CIF and still use an OCI registry. So in the past, many people used to find it convenient to build containers using Docker files and using, like Docker or Builda or something along those lines to build their containers, and then to push their containers up to an OCI registry like Docker Hub or Google Artifact Registry or something along those lines. And then when it came time to run the containers, to pull them and convert them to CIF files using Apptainer. That workflow still makes sense if you're using both Docker and Podman or something along those lines and Apptainer. But it doesn't really make sense anymore if you're just using Apptainer. I would argue that now it makes a lot more sense to actually do your building in Apptainer as well as you're running in Apptainer. And that's because you can still get the convenience of using something like Docker Hub, with Apptainer. So here I've got an example. I have a Rocky Linux repo up on Docker Hub, and this is actually these are signed CIF images, and I'm giving the fingerprint of the signature here, and I'm going to show you why here in a second. So one of the great things that you can do with these signed CIF images that I've got up on Docker Hub is that you can do an Apptainer pull, and you can use this ORAs transport, and then you can pull this Rocky Linux image. And once you've got it pulled, you can use this verify command. Now, anybody can do this. You don't need to have any special public key material on your system. And that's because if you don't have the public key material that you need to verify this container, Apptainer will automatically download it from openpgp.org because I've pushed it up there, and Apptainer is configured to download that. So once you do that, it can verify then that this container has been signed. And now you know that this is an exact bit-for-bit reproduction of the container that I originally built. If you check this fingerprint and the fingerprint matches. Now, why does that matter? Well, going back to this container, what if somebody, is able to steal my credentials, and they're able to replace this Rocky Linux container with one that contains some malicious code? Or what if Docker Hub itself becomes exploited, and people, malicious actors begin to, put containers up that have malicious code in them, or, any one of a number of other things. What if there's a man in the middle when you download this container and you don't get the container that you think? Well, all of those things would result in this container no longer being, verified with this fingerprint. So you can check this before you run that container. Now, you may argue, okay, well, when you built that container, you built that from an upstream container, which was up on Docker Hub or something. And because of that, it still might contain, some malicious code or something you don't know. Well, in this case, actually, if you inspect the definition file, you can see that I actually built this container not from any other container, but I built it from upstream mirrors. So I actually built this container directly from the Rocky mirrors using Yum. And so, of course, I have to trust the mirrors when I build this container, but I would argue you have to trust the mirrors anyway, because you're running an operating system, and your operating system uses the mirrors to control its software. Notice I can use this inspect command now because I downloaded this as a native CIF file. If I tried to look at the definition file of something that I had downloaded in the OCI format, I'd be unable to do so. It wouldn't give me the definition file. Okay, and finally, you can actually check this fingerprint at build time, and here's how you would write a definition file to do that. And so the cool thing about this definition file is that it's going to bomb out, and it's going to result in an error before it gets to actually executing any commands. If this fingerprint doesn't match what it expects from the upstream OCI registry. So this is what this looks like if it works. You know, it goes ahead and it checks while it's building, and if it checks out, then it runs the post section. This is what it looks like if I change the last digit from a 1 to a 2 in the definition file. Now it doesn't get the fingerprint that it's expecting, and before it even gets to the post section, it bombs out and says, no, I'm not going to execute any commands inside this container because this container is not trusted. So I bring all this up because software supply chain is something that as administrators, I think we're going to have to start thinking more and more about. And this provides this ORAS protocol provides a convenient way for you to be able to build like a suite of base containers from upstream mirrors and make sure that they are signed and verified when you actually use them, so you know exactly what's in these containers when you're building on top of them. Okay, and so finally, the last thing I want to talk about is container orchestration. I think I'll cover this fairly quickly. So when we talk about traditional container orchestration, things like Kubernetes, we're typically talking about things that orchestrate services, right? And so what we're interested in with those types of tools is for lots of microservices typically to run that communicate with each other through a well-specified kind of network architecture, and that are supposed to run forever. And then, a tool like Kubernetes is going to make sure that these services come up properly. It's going to check to make sure that they remain healthy. It's going to make sure that, if the VM that supports them falls over, they get migrated to a new VM to continue running, things like that. So this has been hugely beneficial in the cloud native kind of microservices DevOps community. But the problems that traditional orchestration solutions solve are largely not the types of problems that HPC users have. And that's because users are interested in running jobs and not services. And so it's an entirely different problem set. So, but increasingly, users are coming to the realization that they could benefit from having an orchestration tool. And so we're now in a situation which was very similar to what we were in when Singularity first began, in which we're having users come to us and say, hey, can we install Kubernetes on the system? Can we start to use job orchestration? And so now we're at an inflection point where, once again, we need HPC people to come together to build an HPC specific solution for orchestration. And that's what Fuzzball is. So Fuzzball is a container orchestration tool for jobs. So within Fuzzball, you specify a YAML file to run a workflow. And your workflow can be composed of one or multiple different jobs. And those jobs can be dependent upon one another. In this example, I have an MPI hello world, which is running from, so all of your jobs within Fuzzball are running containers. And so here I have this MPI hello world job, which is running from this container, which is up on the Google Artifact registry. We have within the, so this is it's not a public registry. So we have to pass a secret in order to get this container. And that's one of the things that Fuzzball does on your behalf is it manages your secrets. So in this case, I can just use this little template to say, hey, I need this secret that you're already managing in your secret store. Go ahead and get that out and pull this container with it. Once I've got the container, I need to run a command. So in this case, I'll be running MPI hello world. There's a program called MPI hello world in here, which will run. I have to specify the resources. And then finally down here, this little multi-node section is doing a lot of work. So I'm saying that I want this job to be multi-node. I want it to run on 2 nodes, and I want the implementation to be OpenMPI. And that's pretty much all I have to do to run my MPI job within Fuzzball, which is really pretty neat. At the command prompt, if I wanted to run this job, I would submit it with this syntax. So Fuzzball workflow start, and then the YAML file. And then, you know, after it runs, I can get the logs out of it. Here's what the logs look like. I've got a couple of different processes which ran. However, so most users, or many users, might be more comfortable working within a web GUI versus working at the command prompt like that. So pretty much anything that you can do within Fuzzball, you can also do with this web GUI. And this is really great because, so this is, you know, what it would look like to work with that same MPI hello world job that I showed you previously. This is a single job. If you click on it, you get all the different details about it over here. You can change those details, and then you can create a new YAML file. So you don't have to remember all of the YAML specification for Fuzzball. You can actually use this tool to create your YAML files, or you can just submit your jobs directly, you know, from this this GUI. If you submit your job, this is what it looks like. This is the overall workflow. This is the image getting pulled, and then this is the command being run. And then after it runs, you can get the logs just like I showed you at the command prompt, and it'll look something like this. So just really briefly, I understand I'm up on time. But if you, so that was a very, very simple job with just one job. Fuzzball orchestrates workflows. So in this case, we have a really complicated workflow that uses both MPI and GPUs, and jobs run serially, dependent upon one another. There's volumes involved too, so you can map S3 buckets and things like that directly to your jobs. And this is not a real job, but this is just to kind of demonstrate that your jobs can be as complicated as you need them to be. So with Fuzzball, you can create any kind of graph as long as it's acyclic, and your jobs can be dependent upon one another in any way that you want them to be. All right, so just to recap, I covered user namespaces, new recommendations for MPI, ORAs and how it pertains to software supply chain. And then I finished up by talking about orchestration from an HPC jobs perspective. And so I'm sorry that we don't have a lot of time for questions, but I'm happy to stick on for as long as others want to stick around and answer questions. Thank you very much.
It looks like we've got a couple of questions about like pipelines and example workflows in the chat.
Yeah. So can you specify a pipeline of several jobs in series? Yes. So, and I think you probably asked that question before I showed it. And, you know, of course, those jobs can be dependent upon one another. You can do that either with the GUI or with the YAML file. Do you have an example workflow YAML files? Yeah. And in fact, the GUI itself actually has, so I have the GUI here actually up. And if you go to the workflow editor, it's got some examples in it. So you can actually just load a new example file like that. And then you can go and grab the YAML out of it like this. And then once you've got the YAML, you can, you know, you're off and running. So yeah, we do have example files. And then we have task arrays. That's right. So you can have multi-node jobs, which are either MPI, MPitch, or GasNet if you're using Chapel, or you can have task arrays and do high throughput computing, just like you would with Slurm or something like that. How does Fuzzball differ from jobs in Kubernetes? So I would argue that Kubernetes, once again, it has a lot of bits and pieces and things associated with it. It's trying to solve a lot of problems that are problems that, you know, people running jobs don't have. And you could say, okay, well, fine. As a user, you just don't have to use all that stuff. But unfortunately, that's really not the case. As a user, if you're going to use Kubernetes, you really need to learn a lot about a lot of concepts which are not necessarily applicable to you and your jobs in HPC. So I would say the way in which Fuzzball differs is that it's specifically purposely built for jobs instead of trying to take a solution which was built for one thing and trying to adapt it to something else. I mean, it's the same way that we took, we didn't just try to shoehorn Docker into HPC. We specifically built Apptainer, you know, a purpose-built solution for HPC. It's very analogous to that. Okay.
Yeah, I just want to say thanks, everybody. If you need to take off, we're on the hour to get to your next meeting. please feel free to leave. And those that can stick around, and Dave, if you have a few minutes, people I'm sure would like to keep talking if possible. Thanks
Absolutely.
again for all being here. And thanks, Dave, for a great presentation. And we'll follow up with this recording, and we'll follow up with the notes. So, and your slide deck. Thanks, Dave.
Thanks.
Yeah.
Yeah, so I see that Paulo has a question about security scanning containers. This is a really big topic, and it's a complicated topic. I will try to keep my answer short, but excuse me, I could talk about this for a long time. So the short answer is that there are several different products which are available to allow you to scan containers. One that I would recommend, which recently came out, is by the company Anchor, and they have produced a pair of tools. One is called Sift and the other one is Grip. And